it shows the entire electromagnetic spectrum and different parts of it. And different parts are characterized by different range of values of the wavelength of the corresponding electromagnetic wave. So the visual waves, those that we can detect with our eyes, they span a range from 4 times 10 to the minus 7 meters, that corresponds to purple, violet color, right? And then as the wavelength increases all the way up to 7 times 10 to the minus 7 meters, there we have a long wavelength part of the visible spectrum, the red colors. But you can see that the visual part of this entire electromagnetic spectrum is very tiny compared to the entire spectrum, just this range of wavelengths. Okay? Note that the scale here, which gives the wavelength in meters, is not linear. It is so-called logarithmic scale. And usually, when you have to put together on the same graph numbers that differ from each other by orders of magnitude, the linear scale won't do it, because one set of values would be here, and the other set of larger values would be next door on a linear scale. Okay? So for that reason, you use this so-called logarithmic scale, which is often used in sciences, where you can put together values that range from 10 to the minus 12 meters to 10 to the 4 meters, which is 16 orders of magnitude. Okay? So you realize that the wavelengths that we can see constitute really tiny part of the entire electromagnetic spectrum. So you can ask the question, well, why is that so? Why is it that we can see only these colors and we can't see shorter wavelengths, say X-ray wavelengths, or longer wavelengths like microwaves? Well, it has to do with the environment in which we evolved. Okay? We are next to a star, which is our sun, which has surface temperature of 6,000 degrees or so, 5,800 centigrade or 6,000 in Kelvin or absolute scale. And it turns out that the body of any temperature emits the wavelengths of all possible values, except that the wavelengths where it emits most of the energy depend on its surface temperature. So all of us, we have body temperature which is roughly 36, 37 degrees centigrade. That's our body temperature. And it turns out that at that temperature, we all emit most of the energy in infrared. Okay? So to see somebody in the dark, what you need a special goggles with infrared detectors that are sensitive to those long infrared wavelengths, and then the detectors convert that into signal that a soldier or a police officer or a hunter can see with their eyes. Okay? It happens to be that the surface temperature of the sun is such that it emits most of the energy around yellow-green. Okay? So we as a species evolved next to the light source that emits most of the energy at these particular wavelengths, around 6 times 10 to the minus 7 meters. So it was natural just, that our eyes evolved so that they became sensitive only to those wavelengths where the sun emits most of the energy. The sun also emits in X-rays and at very long radio waves. But the intensity of that radiation is much, much smaller compared to the intensity of sun's radiation at visual wavelengths. Okay? If we evolved, or there's anything like that in the universe, say a planet close or orbiting around a neutron star that emits a lot in X-rays and gamma rays, then presumably those forms of life would be more sensitive to these very short wavelengths that are abundant in regions where they have formed. Okay? But we formed as a species next to a star with a surface temperature of 6,000 degrees Kelvin, and it emits most of the energy at these wavelengths. Hence, our eyes are sensitive to these wavelengths. And that's normal, right? If I'm sort of a hunter and in a jungle and a tiger jumps out of the bush at me, I have to be able to react quickly what is happening, right? So I have to have a means to detect them, and he's actually illuminated by the sunlight, and the sunlight is reflected of him. So my eyes better be sensitive to the visual wavelengths produced by the sun. One other thing is that, as you can see in the visible part of the spectrum, the wavelengths are given by very large negative powers when expressed in meters. So it's common to change the unit for measuring lengths when we talk about the wavelengths of visible light, and use so-called nanometers. 1 nanometer is 10 to the minus 9 meters. So then the wavelength of 4 times 10 to the minus 7 meters is then 400 nanometers. And the wavelength of 7 times 10 to the minus 7 meters is 700 nanometers. So this is the visible part of the spectrum, from 400 to 700 nanometers. As we go towards the wavelengths longer than those corresponding to the red light, the first part of the spectrum, up to about a millimeter or so of wavelengths, corresponds to infrared radiation. Then at even longer wavelengths, we have microwaves that are used, say, in radars, right? When the cops are chasing the speeders, they have a radar gun which just produces a pulse of microwaves that bounces off the car, and then using the Doppler effect, which we'll talk about later on in the course, it basically is able to determine the relative speed of the vehicle and decide whether you are speeding or not, right? Microwaves are also used in telecommunications for cell phones and so on and so forth. Then at longer wavelengths, you have radio waves, either FM at shorter wavelengths or AM in the longer wavelengths. And then if we move now in the opposite direction to wavelengths shorter than those corresponding to violet light, then we have UV, ultraviolet radiation. Then at even shorter wavelengths, we have X-rays, and then even at shorter wavelengths, we have gamma rays. But they're all just different parts of one and the same thing, and that is the electromagnetic field. The only difference between different parts is the value of the wavelength. That determines whether it's a visible light or microwave or UV or gamma rays and so on.